Okay, hello everyone in a new video. Then we have reached part 4 of chapter 8, which is the chapter of mechanical actions in the third unit of mechanics. And we have reached section 25, which is given by the electric force. Then let's recall from part 3 that we have discussed whenever we have a mass, the object will be directly subjected to the weight. Whenever we have a string or a spring, then the object will be directly subjected to the tension. Now in the following document we have a solid of mass m, then it will be directly subjected to the weight. And because we have the string, this string which connects the support to the ball, then we have the tension. So notice that the tension, because it's classified as a contact force, then the point of application will be the point of contact between the two bodies that are at interaction. They are given by the string and the solid. So, and notice that T is represented along the string, and this is extremely important because the line of action is T is always along the string. Now, what is S is shifted to the right due to the action of an electric force exerted by this metallic rod on the solid S. Okay, so now let me write down the electric force Fe exists due to electrically charged rod or let me say now in this case, in general, due to a charged bodies. So whenever charge exists, we should think of the electric force. Now consider the following example. An object arm connected to a string fixed to a support So this is the solid as connected to the string, and the string is fixed to a support. Here we have a charged body. This is positively charged. Now in addition, to its weight W, in addition to its weight and the tension in the string, M is subjected to an electric force due to a positively charged rod. So now, independent of the charge of the solid S, here what is important for us that the action of the rod on the solid S caused the solid S to be shifted to the right, and this action is being represented by this force. Now, why we have represented the force Fe from the center of gravity G? Because recall that the force Fe is electric force, and we know that the way the electric and the magnetic are classified as acting at a distance, and in this case the point of application will be the center of gravity G. Now based on this document we need to complete the following table. Let me start by the weight. So it has the point of application, which is the center of gravity of M, which is G. Then let me say center of gravity G. Now the line of action is given by vertical and the direction is downward. So as usual, always these three properties for the weight are always fixed. Now the tension. So the tension is a contact force, and the point of application will be the point of contact between the two bodies that are at interaction. And in this case, the string and the solid are at interaction. So this is the point of contact, which is A. Then let me say point of contact. Between the object and the string, which is A. And now as for the line of action, so we always start by writing along the string. And by the line of action we mean whether it's oblique, vertical, or horizontal. In this case this is oblique. And as for the direction, it is upward to the left. Now as for the electric force, I repeat, because this force is classified as an acting at a distance, then the center of the point of application be the center of gravity G. Now as for the line of action and the direction, so in order to determine the line of action and the direction, we can use the following trick. Is that you connect, so if this is the center of gravity of the rod, so you connect the center of gravity, you connect both center of gravities. So in this case this is the line of action of the force. So I repeat, in order to determine the line of action of the electric force or magnetic force, as we shall see later, you connect both center of gravities. Then the line of action in this case is horizontal. And in order to determine the direction, you follow the direction along which S has been shifted. So notice that S has been shifted to the right, which means that the direction is to the right. For this reason, we have represented the vector force Fe in the following way. And now let me move to the other section, which is the magnetic force. And this section is given by 26. Then here what do we have? We have a solid S which has a weight, which has a mass, then it will be directly subjected to the weight. We have a string, then there is a tension. Now instead, compared to the previous case, we had a rod. Here we have a magnet, then it will be subjected to the magnetic force. Now let me write here the magnetic force Fm is due to magnets in general. Then this is in general. Now let me consider the following example. In which we have an object M connected to a string. fixed to a support. So this string is fixed to the support. And now, in addition, so we have the weight and we have the tension, and in addition to these forces, we have the magnetic force. Then M is subjected to a magnetic force. So how come we represented Fm in the following way? So the trick is that to connect the center of gravity of both objects. So if this is the center of gravity of the magnet, then if you connect them like this, so notice that in this case Fm is in the horizontal, along the horizontal. Now we need to know whether it's to the left or to the right. Notice that S is being shifted to the right. For this reason, the line of action is to the right. Now let's complete the following table regarding the characteristics of these three forces, excluding the magnitude. Starting by the weight, as usual, the weight has three fixed properties, and they are given by the center of gravity G. The line of action is horizontal, and the direction is to the right. Sorry, the line of action is vertical. And the direction is downward. So always the weight acts on the center of gravity vertical, downward. Now regarding the tension, because it's classified as a contact force, then the point of application will be the point of contact between the string and the solid. So it's the point of contact. Between the object and the string A. Now as for the line of action, it is meant whether vertical, horizontal and oblique. So in this case it is oblique, and let's say first along the string. Oblique. Now as for the direction, notice that it is upward to the left. And now as for the magnetic force, so because the magnetic force is classified as acting at a distance, because it is one of the three forces that act at a distance given by the weight, the electric or the magnetic, then the point of application will be the center of gravity G. Now the line of action in this case, it is horizontal. And the direction is to the left. Sorry, to the right. Because notice that the arrow is pointing to the right and the solid S or the solid M is being shifted to the right. And now we have reached section 27, which is the friction force. So now what are the different forces acting on the solid S? Because it has a mass, then it will be directly subjected to the weight, which is vertical downward. We have a support, so the solid S is resting on the support, then there will be the normal reaction, and we refer to N to be the normal reaction because it is perpendicular. The word normal means perpendicular, so this is the normal N. And now we want to discuss a new force which is given by the frictional force, and this force exists whenever there is a rough surface. So there is a rough surface between the solid S and the support. And let me write here the friction force is the force F that opposes the motion of the object. So what do we mean by this statement? Now here, suppose that the solid S or the solid M is not falling down. What is preventing the solid M from not falling down is due to the friction force between the solid M and the inclined plane, which is rough in nature. Then M is supposed to fall downward like this. Then the friction force will try to oppose this action. Then it will be, if this is downward to the left, then this force will be upward to the right in order to cancel the effect of this force. And usually the force F is present whenever we have a rough surface. Now, why we have represented the force F from the point A? Because notice that F is not weight nor electric nor magnetic, so it's a contact force. Then the point of application will be the point of contact between the solid M and the inclined plane. The point of contact between the solid M and the inclined plane, which is the point A. Okay, and why we have represented F in this way, oblique, upward to the right? Because we know that if the force of friction was absent, I mean not present, then the solid S will slide along the inclined plane like this. So the properties of the force F will be exactly opposite to this arrow, opposite to the motion. For this reason, we have mentioned that the friction force opposes the motion of the object. Now let me state here the reason behind the friction force, and let me say it is due to a rough surface. And then an object arm rests on a rough inclined plane. Now the object arm is subjected to the weight the normal reaction and the friction force. In this case, the friction force prevents the solid from sliding down on the inclined plane. And now let's complete the following table. Then as for the weight, we know that the point of application will be the center of gravity G. And this is vertical. And this is downward. Now as for the normal reaction, we know that the normal reaction is a contact force, so the point of application will be the point of contact between the two bodies that are at interaction, and this case is given by the solid S and the inclined plane, which is, the solid M and the inclined plane, which is the point A. And now as for the line of action, we know that always the normal is perpendicular to the support. And in this case, because it's perpendicular to the support, then the line of action is oblique. Now as for the direction, it is upward to the left. Now as for the friction force, we have justified why the friction force is like this. It's not the weight nor electric nor magnetic, so it's classified as a contact force. And in this case, the point of application will be the point of contact between the solid M and the inclined plane, which is the point A. Now, as for the line of action, it is oblique. And in this case, the direction is upward to the right. And by this, we are done with the explanation of this chapter. Now we can move on to different exercises. Let me start by the following. Then in each of the following cases, exercise 12, section 28, represent without a scale all the forces acting on the mass M that is at rest. So let's consider number 1. Now here, because we have a mass, then it will be directly subjected to the weight. Because we have a string, then it will be directly subjected to the tension like this. And because we have a normal reaction, then it will be subjected to the normal reaction. So always the weight is from the center of gravity like this. Now the tension will be represented like this along the string, and the normal reaction is perpendicular to the plane like this. Now as for the second figure, let me explain it. M is supposed to fall down, but what is preventing it from falling down is the magnetic force. Now we have the weight because it has a mass. Because there is an inclined plane or support, then it will be subjected to the normal. And because it has here there is a magnet, so we suppose this is an iron which can interact with the magnet, then it will be subjected to the magnetic force. In order to know the line of action and the direction of the magnet, we connect both center of gravities. So in this case, this dotted line represents the line of action of the magnetic force, which is horizontal, and the direction will be toward the magnet, which is upward to the right. Then let me represent the forces. Here this is the weight, this is the normal, and this is the magnetic force. Notice that I have represented the magnetic force from the center of gravity, G of M. This is the normal, this is the weight, and this is the magnetic force. Now as for the third figure, here because it has a mass, then it will be directly subjected to the weight. Because we have a string, it will be directly subjected to the tension. So notice that in this case we have represented T from this point, and also we have represented T from this point. So always the tension is represented from the point of contact or at the end of the string. So this is the weight, this is the tension, yet we didn't finish. Here notice that there is a magnet, then it will be directly subjected to the magnetic force if this is an iron. How to determine the line of action of the magnetic force? We connect both centers of gravity, then this will represent the line of action. Because the solid M is moving, it's supposed to be moved to the right, then the magnetic force will be like this. Now other than the magnetic force, here there is a support, otherwise the magnet will move more toward the right. So what is preventing the solid S from moving to the right? A normal force due to this support, which is like this. How come I know that the normal is like this? Because always the normal is toward the object and perpendicular to the support. So here there is a magnetic force like this. And there is a normal force like this. Now as for figure number 4, here because we have a mass, it will be directly subjected to the weight. Now here we have two supports, this one and this one. So we have to support a two normal reaction. The first one is at this point, perpendicular to the support, which is like this, and another one at this point perpendicular to the support like this. Then let me represent the forces. So this is N1 and this is N2. Now as for number 5, because this car M has a mass, then it will be directly subjected to the weight from the center of gravity of the car. And now here we have the car is being in 3 dimension, then it will be in contact with 4 points, because we suppose that the car has 4 wheels. But here only 2 wheels are apparent for us. Then we have 2 normals at the wheel of each car. This is N1 and this is N2. Now as for number 6, we have a car, then it will be directly subjected to the weight, which is like this. We have the car is being in contact with the inclined plane in 2 points. So we have 2 normal reactions like this. This is N1 and this is N2. This is the weight. Now because we have a rough surface, then there will be a force of friction between the wheels and the rough surface. So how to determine the line of action of the friction? The car is supposed to move like this, then the friction will be like this, opposite to the supposed direction of motion. So here we have first the force of friction F1 and here another force of friction F2 like this, and let me represent them. Now as for number 7, so here we have a solid of mass m, then it will be directly subjected to the weight, and because we have a spring, it will be subjected to the tension like this. Now as for number 8, then this solid has a mass, it will be directly subjected to the weight, and because we have three tensions, three strings, then it will be subjected to three tensions like this. So this is the weight. This is tension T1, tension T2, and tension T3. Now as for number 9, here we have this solid and this solid, but we need to represent only the forces acting on the solid. We don't care about this. So first of all, we have the weight, which is like this. Now I will shift a bit the weight just in order to draw. So suppose that here the center of gravity G. So this is the weight W. Now here, because we have one string, 2, 3, then we will have three tensions. So this is the first tension, this is the second tension, and this is the third tension like this. Now it's left to determine the directions, so they will be always away from the object. So this is like this, and this is like this. Then this is T1, T2, and T3. This is it for exercise number 12. Let me move now to the next exercise, which is exercise number 13. They are telling me the spring R is suspended vertically with its upper end O fixed to a horizontal support. Its lower end A carries a solid S of center of gravity G of mass M is equal to 0.5 kilograms. The solid S is then submitted to two forces, its weight W and the tension T. Given that the G is equal to 10 newtons per kilogram, then the moment we have the mass and the moment we have the weight, then we can directly determine the magnitude of the weight, which is M multiplied by G. Number 1, indicate for each of these forces if it's a contact force or force acting at a distance. We know that the only three forces act at a distance given by the weight, the electric, the magnetic, so then the weight is one of them. And all other forces are classified as contact forces, and in particular the tension T. Now in number 2, they are telling me indicate the point of application, the line of action, and the direction of W. Then we always know that the first three properties of the weight are always fixed and they are scene independent, and we shall always list them in the following order, starting by the point of application, which is the center of gravity G. As for the line of action, it is vertical, and as for the direction, it is downward. Now in number 3, they are telling me to calculate the magnitude W of the weight W. Then W, because we have the mass and we have G, can be directly determined from M multiplied by G, which is 0.5 multiplied by 10, which is equal to 5. Since M and G are expressed in the SI, so the value of W will be in the SI, which is in newtons. Then this is it for this exercise. Moving to the next exercise, which is exercise number 14. A solid S having the shape of a cube of side A is equal to 10 centimeters. Knowing that centimeters is not the SI unit of length, in order to convert from centimeters to meters, we divide by 100. Is placed on a very smooth inclined plane, so whenever they tell us smooth, then it is not rough, which means that the friction is neglected, as shown in document 1. They mentioned this document, now we can use it. Now, I wanted also to mention that the solid S, because it has the shape of a cube, then it's classified as a regular shape, then its volume can be calculated via a to the power 3. And the density is given by 2000 kilogram per meter cube. Now notice the following. Because we have A, then we can directly determine the volume. Because we have the density, we can deduce the mass whenever one calculates the mass and it's given that the value of g is equal to 10 newtons per kilogram, we can determine the magnitude of the weight. Now in number 1, calculate the volume V of S because it's a regular shape. Then 0.1 to the power 3, and this is equal to. So plugging this on the calculator, we always use the SI unit, then this is given by 1 times 10 to the power minus 3. Since this is expressed in the SI, so the value of V will be in the SI, which is meter cube. Then V is equal to 1 times 10 to the power minus 3 meter cube. And now as for number 2, show that the mass of S is M is equal to 2 kilograms. Then because we know the density and we know the volume, the mass can be determined from the following relation. Here we are using capital M. Now constructing the triangle of this formula. Here because we have divide, then this is rho, mv, rho will be at the bottom. Putting our hand over m, then m is given by rho multiplied by v. The value of rho is given by 2000. And the value of v is given by 1 times 10 to the power minus 3. Plugging this on the calculator, then the value of m is given by 2. Since both rho and v are expressed in the SI, so the value of m will be expressed in the SI, which is kilograms. Then the mass is equal to 2 kilograms. And now in number 3, calculate the value W of W. So by the value they mean the magnitude. Always value is another word for magnitude, another expression. So the weight is equal to m multiplied by g. The value of m is 2. And the value of g is 10. This is equal to 20. Since both m and g are expressed in the SI, so the value of W will be in the SI, which is in newtons. Then W is equal to 20 newtons. Now in number 4, they are telling us give the line of action and the direction of W. We know that always the line of action of W is vertical. And the direction is downward. Now in number 5, they are telling us redraw document 1 and represent on it W using the scale 1 centimeters corresponding to 5 newtons. And by represent, it means that we need to draw the vector. In order to draw the vector, we need to determine the length of the vector. So we know that the magnitude of this vector is 20 newtons. Then using this scale, one can determine the length of this vector. So 1 centimeter corresponding to 5 newtons. Then 20 newtons corresponding to how much? This value here will represent the length of the vector. Then 20 multiplied by 1 divided by 5, this is equal to 4 centimeters. Now let me sketch again document 1. And let me here, so this is the center of gravity G. Let me draw here a vector given by 4 centimeters like this. So this is the weight. So each grid here represents 1 centimeter, then 4 centimeters corresponding to 20 newtons according to this scale. Now as for number 6, S is submitted to its weight W and another force. Give the name of this force. Okay, so here because we have an inclined plane, so it will be directly subjected to the normal reaction. Then the other force is the normal reaction N. And specify for each of them whether it's a contact force or a force acting from a distance. So we need to specify for both forces the weight and the normal reaction. Then let's start by W. We know that the only three forces that act at a distance are given by the weight, the electric, the magnetic. Then the weight is one of them, so this is acting at a distance. And all other forces are classified as the contact forces, and in particular the normal reaction is one of them. And now let's move to the final exercise in this video. They are telling us we suspend a mass of 0.2 kilograms from the end of spring balance. The spring balance indicates 2 newtons. We repeat the measurement again for the following masses. The aim of this exercise is to calculate the gravitational field strength via two different methods given the following table. So they are telling us draw the curve corresponding to the variation of W as function of M. So let's recall how do we plot a curve. We always start by representing the x-axis, then representing the y-axis like this. And you know that always in physics, axes are labeled by physical quantities. Here we have two quantities, we have the mass and the weight, so we have two choices. Either we place the weight here and the mass here, or the mass here and the weight here, and this is very critical. From the early beginning, we need to be specific in labeling these quantities, these axes. And this can be done using two different methods. The first one is referring to the title. They are mentioning the variation of W as function of M. So the first quantity coming after the variation will be represented here. So this is weight in newtons. And for sure the other one will be M in kilograms. Now the other thing is referring to the scale. They are telling us along the y-axis, so 1 centimeter is for the grid, but notice that it's being referred to the 0.1 in newtons, which means on the y-axis there must be newtons. And as for the x-axis, they are telling us 1 centimeter, this is for the grid, and 1 kilogram for the axis itself, which is in agreement. Now let me specify the scale here. Then the scale is along the x-axis. We have 1 centimeters corresponding to 0.1 in newtons. And as for the y-axis, we have 1 centimeter corresponding to, this is 1 kilogram. As for the y-axis, 1 centimeters corresponding to 0.1 in newtons. And now let's divide the scale. On the x-axis, for each 1 centimeter, we have 0.1. So here there's something wrong. Let me correct it. So this must be 1. And this must be 0.1. Now it is correct. So we will move 0.1 on the x-axis. Each centimeter we will add 0.1, 0.2, 0.3, 0.4. Now we need to stop at some point. This point, which is the final point, is usually referred to the table. So notice that we will stop at 0.6. And in this case, we can minimize the graph to here. And now as for the y-axis, each 1 centimeter will add up 1. Then this is 1, 2, 3, 4, 5, 6, which is the final value on the table. Now let's plot the points. For 0.2 we have 2, this is the first point. For 0.3 we have 3. For 0.4 we have 4. For 0.5 we have 5. And for 0.6 we have 6. So in this case, these are the points. And now we can connect them. And in this case, the shape of the curve is a straight line passing through the origin. Now, the only thing missing here is the title. And the title can be extracted from the question corresponding to the variation of W as function of M. Then this curve represents the variation of W as function of M. And now we are done with number 1. And number 2, they are telling us first method, because recall that the aim of this exercise is to calculate the gravitational field strength is G via 2 different methods. Now write down the relation that gives us the gravitational field strength if we know the mass and the weight, and this is given by W is equal to M multiplied by G. Now in 2.2, determine from the graph the weight corresponding for 0.45 kilograms, and because we are using the graph, then we should use it graphically, and this word usually they give it half a mark. Then for M is equal to 0.45 kilograms, we have then 0.45 kilograms correspond for this point on the curve, and if you are plotting on a graph paper, it will correspond to a value of 4.5 newtons. Now in 2.3 they are telling us deduce the value of the gravitational field strength, and by deduce it means that we need to use the previous part. In the previous part we have determined a specific value of M specific value of W corresponding for this M, and using this relation we can determine the value of G. Then W is equal to M multiplied by G, and we are interested in determining the value of G, constructing the triangle of this formula here. Because we have multiplied, then W will be at the top, M and G here, putting our hand over G, then G is equal to W over M, which is equal to 45 over 4.5, then this is equal to 10. Since both W and M are expressed in the SI, so the value of G will be in the SI, which is in newtons per kilogram. Then G is equal to 10 in newtons per kilogram. Now in number 3, second method, they are telling me calculate graphically the value of the gravitational field strength. And here, because it's a direct question, this can be calculated using the graphical method, which is the slope. And the slope consists of 4 steps. The first step is by writing the definition. Then let me say the gravitational field strength is equal to the slope of the characteristic. So usually we used to say current voltage curve, now we will say mass weight curve. Now we are done with the step number 1. Step number 2, to choose any 2 points belonging to the curve. We can choose A and choose this point to be B. Let me write the coordinates of these points. A, we start by the mass, which is 0.1 kilograms, and by the weight, which is 1 in newtons. As for the point B, it has a mass of 0.5 kilograms. As for the weight, it is 5 newtons. Now notice that all of these are in the SI, so we can directly skip step 3 and calculate the value of G, which is given by the weight of A minus the weight of B over MA minus MB, and here we need to respect the order. In the numerator we have started with A, then in the numerator we have started with B, with A. So in the numerator and in the denominator we must start with the same point and end with the same point. So the weight of A is 1, the weight of B is 5, over 0.1 minus 0.5, and this is equal to 10. Since all of these are expressed in the SI, so the value of G will be in the SI, which is in newtons per kilogram. Then the value of G is equal to 10 newtons per kilogram. So that's it for me in this video, guys.